to do when it's cool enough to form our particle, the proton, which has just been born. So we're going to follow this proton throughout its life cycle in order to try and answer our questions about dark matter. Okay, so lots of boring stuff happens. Matter gets together, it forms gas clouds, these form stellar nurseries, the matter clumps through gravity, it heats up, it produces different elements, and then finally later on you get the formation of galaxies, stars and planets, and civilization as we see here. And the invention of Belgium and jam. But something really interesting happens in 1954. After the terrible conflict that ended in 1945, Second World War, scientists and politicians around Europe got together and they said, we never want that to happen again. So, we need to do everything we can to stop it. And what we need, given that both world wars have started in Europe, what we need is something, a centre of stability, a beacon, that will help provide political and military stability throughout Europe. And so they invented a common goal for all Europeans and European scientists, and that goal was CERN, where scientists from different countries could go and all work together on a common scientific project. The governments would have to each pay into CERN in order to keep it going, but it would be a common project that everyone worked on collaboratively. So let me introduce CERN now. So this is our galaxy. If we go into one of the outer arms, sort of 2/3 of the way along, we might find our sun and then our Earth, which is here. And what you can see, we're zooming in on now, that moustache-shaped lake is Lac Léman, and we have Geneva just a few miles away from it, just on the border with France. And if you fly in to Geneva, you won't see this white line, which is on the circle on the surface, because of course that's where the beam line of CERN is. So it's 100 metres underneath the ground, but we've just drawn it on the surface here. Okay, so it's big. It's about the size of the Circle Line. It's 18 miles circle. So this is the biggest man-made experimental, biggest machine that exists. It's very impressive. If you ever go to Geneva, a few weeks before you go, get online and go to the CERN website and book yourself a free guided tour around CERN. There's about 20 a day. All CERN scientists who are volunteers will take you around. If you can, you'll go down to the experiments. That depends on whether it's running or not. So at the moment, it's running, and you won't be able to go down. There's plenty of other stuff to see, and some stuff on the surface, some experiments on the surface that you can see. So I really recommend that. It's well worth a look. Okay, so this 18 kilometres, 18 miles around tunnel looks like this. There's one of the maintenance crew on a motorised tricycle going around. And this thing in the blue there, that's absolutely blue, that contains two beams of protons going in opposite directions. And that's basically what the Large Hadron Collider is. It's a system of beam flights that goes all around the circle. Okay, so you can see that it's about the size of the Circle Line because the curvature of the tunnel is roughly the same back station as it is to CERN. Okay, so remember it's 100 metres below ground. Why is it 100 metres below ground? Well, that's because we want to shield everything from ordinary radiation that you get on the surface, which comes from space. Right? There's cosmic rays coming down. If you put it 100 metres below the rock, nearly all of that cosmic radiation is filtered out in the rock. And so when you measure things, your data basically. So you see the experimental halls, where there are caverns carved out of the rock in various places. That's where the actual experiments take place. So if we look down on a kind of map of CERN, it looks a lot more complicated than just this one circle that I was talking about. The circle is the big one at the top, so that's the thing that's 18 miles around. But you can see that actually it requires a complex of different accelerators. And in fact, what we're going to do is start right here, which is where everything begins at CERN, in the Large Hadron Collider. And at the moment, I'll take questions again. If there are any, yeah. Yeah, good question. So the question is, what experiments do you do? So what we do is we take these beams of protons and you cross the streams. I'll show you actually, it's on the graph. So in a way that I'll explain in a minute, you get them spinning these proton beams at high energies. They're going around in opposite directions in a big circle. And where there's like a yellow star, that's where the streams are crossed and the protons are slammed into each other. And what I call an experiment is a machine that you build around the outside of that crossover point to measure what comes out, basically. So that's the basic thing, but we'll go more into that in the talk, yeah.
So if they're getting quite close to the speed of light, is that important for the rest of the
So the question is, these beams getting close to the speed of light, is that important because of time dilation and so on? And yeah, it is. The main thing that you're after, though, is the energy. Because what we need is high energy, and I'll explain why later. But it's true, okay, protons last for a very long time, so it's not like with some other particles, for example, muons, they decay away unless you sped them up really quick and slow time down for them. But protons aren't like that. Yeah. One at the back. Yeah, okay, so the question was, what people thought that the Large Hadron Collider might create a black hole. Why was that? So what happened was, to guys in Hawaii, I think those were biologists, they sued the US government for supporting CERN because they said, oh, we've heard about this possibility that it might produce a black hole and destroy the Earth. Okay, so then the press got hold of it. CERN PR division made an explicit decision to really engage with this story because they thought, well, okay, what we're going to do is be really open about everything. We'll set up a panel to discuss this possibility, like a mini black hole, really tiny atomic-sized one. And people are writing scientific papers about this. The thing is, they wouldn't behave like one that you've seen in Interstellar, or whatever that's an astrophysical black hole. These smalls would just pop immediately, but it'd be really exciting because it'd be a signature that there's an extra, a full space dimension, right, that's going to go up on itself. Now, what CERN did was said, well, we don't know whether we're going to be able to produce these mini black holes or not. We think they would be safe even if we did, but actually let's not just rely on theory. Let's use observations and evidence to make sure that it's going to be safe. And basically, what we need to know is that the moon has been around for the last 5 billion years, and nothing bad's happened to it, because there are cosmic rays with protons in it, slapping from the moon with huge energies, same energies as they have in the galaxy, and actually something more as well. And nothing bad has happened. So even if a few black holes are being produced on the moon because of the cosmic rays hitting it, it's not swallowing the moon up. So I mean, there's no doubt that it was going to be safe. Good question. Okay.
Let's stop for a minute. How do you actually get them?
Very good question, and I'll show you that now. So, that's where we start with the protons. So, our protons are basically it's born actually out of the Big Bang source ago. It really formed 1 second afterwards. It's been the creation of Belgium and Jam and the Sun, and somehow it's ended up in this bottle of hydrogen here, 100 meters underground in CERN. So what happens is this valve is automatically opened at the top, and a few billion of these hydrogen atoms are sucked out the bottom, and then the valve shut again. That gas is then heated up. It's ionized with electric fields, so the electrons go one way and the protons go another way. So you extract the protons off, and then what you do is you spin them up. Well, actually, you start off with a linear accelerator. So you've got the protons in a little tube, and with electric and magnetic fields, you kind of speed them up. And you feed them into a ring, which is called the proton synchrotron here, and they're sped up there in the proton synchrotron again, kicked by electric fields and focused by magnetic fields to 87% of the speed of light. And then they're gradually skimmed off and fed into a bigger ring, this SPS ring, where they're sped up further, and then they're skimmed off and fed into the big ring in each counter-rotating beams in each direction. And as you probably noticed, they're going in light cycle at like 99% of the speed of light by then. So that's basically how it works. Okay. So, so if we think about these protons, actually what happens is we have a few meters long length of the beam pipe has these protons in. This is an artist's representation of it speeding down the beam pipe, which is vacuum, in a vacuum. They're kicked along until they get to one of these crossing points. Now, there's a few meters long of protons, then there's a gap in the beam pipe, and then there's another few meters long of protons, and each of those lengths is called a bunch, right? So you have thousands of these bunches of protons going around the ring in each direction. And this isn't to scale. Actually, the protons are really, really tiny. And they're focused in a beam which is sort of a millimeter across, but still, they're nearly all space, right? There's only tiny little dots. So when you cross the streams, nearly always these protons just zoom past each other. So if you look at any proton, it's very unlikely to hit another one when you cross the streams. But usually when a billion protons goes past a billion other protons, a couple of them will bump into each other and interact. And so that's what you're there to measure. They collide into each other, and they go into 1,000 fiery fragments, which you measure by building one of these detectors around it. You want to measure various properties of these fiery fragments and do kind of detective work to go back to the moment that they hit each other and try and work out exactly what's going on there. So this is answer to your question about is it speed or is it energy that counts. It shows you the different accelerators like the Large Hadron Collider that have happened since 1960. And on the vertical axis, so year of first switch on is on the horizontal axis, so on the vertical axis is the energy of the beams. And what you need to know is each time you go up to one of these horizontal lines, the energy goes up by a factor of 10. So here you have 1 billion electron volts worth of energy, here it's 10 billion, then 100 billion, then 1,000. And the Large Hadron Collider is way up here on the right-hand side, and back here we were only doing 1 billion electron volt collisions, whereas now we're doing 1,000. So this is pushed to go higher and higher in energy. And why is that? Well, the reason is basically because you want to discover new fundamental particles and find any ones that exist, and forces too between them. And what you do is you use Einstein's famous equation E equals mc squared, right? So E is the energy, which is of the beams. What you try and do is turn that into mass. So you try and produce successfully heavier and heavier fundamental particles by turning the energy of the beams into mass. And the idea is, during all of last century, there were many new particles discovered, because down here, perhaps you didn't have the energy to produce a particle that's got a mass 10 times this amount, but by the time you get up here, you can produce it. And that's one of the reasons why the Higgs boson wasn't discovered before, for all of these experiments. It's just too heavy. It's 125 times the mass of the proton. That's too heavy for all of these previous experiments to find. Okay, so these detectors that we build around, that have been built around the crossing points, act as 3D digital cameras, basically. They're really complicated beasts. There's lots of sub-detectors, and they're in a vaguely concentric counter-cylindrical pattern. This is one of them that's incompleted, which is the Atlas detector. As you can see, these are people here, so these things are huge. The cavern's 40 meters tall. So if you go down there, it does look like a Bond villain's lair. It's really fun to go down. But you can see these big structures here are spiral toroid magnets. So they're kind of solenoidal magnet system that produce a great big magnetic field, very strong magnetic field throughout the whole structure. And the way that these fiery fragments curve in the magnetic field tell you the charge of the particles, the curvature tells you what the energy of the particles is. And so by using these machines, you can find out all of the things that you want to know about these 5 fragments that are coming up with the collisions. So, are there any questions? Yeah.